Hello, and welcome to another day of the Internet Measurement Village. Joining us today, we're very happy to have Kevin Bock from the Geneva project, and he'll be telling us all about evolving censorship evasion. Thanks for joining us, Kevin.
Thanks, Arturo. Hey, everybody. My name is Kevin Bock. I'm from the University of Maryland. I really just want to say a huge thank you to all of the UNI organizers, everyone who put together this entire conference. It's really been an awesome experience to be able to join in on. So today I'm going to be talking about automating censorship evasion and what we've been working on in this space. Many of you know this already, but in-network censorship by nation states is one of the most pervasive forms of automated censorship that operate around the world today. Some nation states, they operate censorship a little bit like this, where the censor is physically inside the network path. But in practice, it can often be difficult for them to get censors on all of the network paths. So instead, the way many censors operate is more like this. So instead of being inside the path, they're on the path. And instead of being a man-in-the-middle attacker, this makes them a man-on-the-side attacker. And there are some really interesting implications for censorship evasion research when you have a threat model like this. So let's see an example. Let's say we have a user, let's say in China, and he's our client. And they're going to try and reach some forbidden resource, let's say Wikipedia. And they're going to make a request. And this request will move through the network. And you'll notice the server will get the packet, and the censor will too. But the censor only gets a copy of the packet because it's on the path. It's not inside the path. So if the censor wants to censor this connection, this particular censor, it can't just drop the packet because it's not in the path. So instead, what it's going to do is it's going to inject its own packets into the connection stream. So specifically, what it's going to do is it's going to inject spoofed TCP reset or teardown packets. These are normal packets. Our computers send these all the time, and they basically just exist to tell the other side of the connection, stop talking to me. What the censor is going to do in this case, it's going to send two copies of this packet, one in each direction. It's going to send one to the client, pretending to be the server, and it's going to send one to the server, pretending to be the client. What this is going to do is the client's going to get this packet, and it's going to think, well, the server just terminated our connection. And the server's going to get this packet, and it's going to think, well, the client wants to stop talking to me. And just like that, censorship has been achieved. Both sides have stopped talking to each other immediately. But if you think about this, in order for a censor to pull off this attack, the censor requires information about the connection. It needs the port numbers, the sequence acknowledgement numbers, etc., which means that the censor needs to be tracking per flow state. Now, if you're a censor and you're trying to track state at the scale of a nation of China, you're going to inevitably have to take some shortcuts along the way, or write bugs. And we as evaders can take advantage of some of these shortcuts. So I'll give you an example of what one of these shortcuts, how we can take advantage of one of these shortcuts that has been used in prior work. So here we have, once again, our client going to make a forbidden request to the server. But before we send our request, we're going to inject our own TCP reset packet into the stream. And we're going to do it in such a way that we set the TTL, or time to live. This is a field in the IP header that controls how long a packet will live in the network, and it decrements once per hop. So we're going to set the TTL high enough such that it reaches the censor, but not so high that it reaches the server. So for this diagram, we'll set a TTL of 2. And we send this packet, the packet's going to move throughout the network. And just like before, the censor is going to get a copy of the packet. But in this case, because we set the TTL too low to reach the server is not going to get the packet. It's not going to reach. It's going to get dropped along the way. Okay. Now, again, the server never saw this packet. But when the censor sees it, the censor is going to say, well, it looks like the client just terminated its connection, so I can stop tracking it now. And we'll throw away the state it's been tracking of this connection. Now, when this happens, we are free to communicate for the rest of this flow, client to server, censorship-free. Now, this is just one example of one of these such shortcuts and how we as invaders can take advantage of them. And over time, over the last 10, 20 years, evaders have come up with a number of these such techniques. The problem with these is a lot of them no longer work. Over time, as researchers have been developing them, censors have been updating themselves and patching them out. And the problem with this is it really comes down to how we've always approached research in this space. And the way we've done this has always looked a little bit like this. So we make hypotheses, we take measurements, and even as tools like UNI, IceLab, Censored Planet, et cetera, have been crushing it in the measurement space, we still need us human researchers to consume that data, make hypotheses about what's going on. And we do these iterative cycles of we take measurements, we make hypotheses, and we build up a good mental model and understanding of how these sensors are operating. And then after the fact, once we have this understanding, we can apply our good human intuition and then create some sort of evasion strategy and evade censorship. And this has basically been the MO for censorship evasion research for the past several years. The one problem with this is it's a largely manual effort. And the reason this is a problem because it gives censors an inherent advantage. And the reason for this is, to us, censors are a black box. We don't get to see their code. They're not open source. So when we find a bug, the way we do it is we have to poke at these black boxes and get a good understanding. But for them, they can just read our blog, see our tool, check out our paper, and they can go update themselves. And often it can be the case that it's faster for censors to update themselves than it is for evaders to find new techniques. And this sort of asymmetric information disadvantage was the genesis of this project. So we wanted to ask the question, how could we give evasion the advantage in this research space? So what I'm here to talk to you about today is how we've been trying to turn this problem on its head. And specifically what we've been doing is automated or AI-assisted censorship evasion research. And our model looks a little bit like this. So at the start, we use some sort of AI learning system, fuzzer, to automatically learn a new evasion strategy and let evasion happen at machine speed. And at this point, we can just be done. We can take what the AI has learned, we can apply it in the real world, and just like that, we've defeated censorship at machine speed. After the fact, we as researchers can then go back and use the strategies that the system has identified to understand how the censorship works. So instead of our understanding being a blocker, it's something that can happen after the fact. Now, this can sound a little ridiculous. We've actually built this system. We call it Geneva. It is a genetic algorithm. Its name comes from genetic evasion. So for the rest of this presentation, I'm going to show you guys how we built Geneva, walk you through some of the strategies Geneva has found, and if the demo gods are with us, I'll even show you a demo of it working live. So Geneva is a genetic algorithm, and a genetic algorithm is a biologically inspired system. So if you want to build a genetic algorithm, you're going to need a couple of things. And I'll walk through these briefly using us humans as examples. So first, you're going to need some system of building blocks. So for us, we have our building blocks of our DNA, just our DNA bases, ACTG. Once you have these building blocks, you need some sort of way to put them together and compose them in a way you can build and manipulate from there. So you need some sort of composition. Now for us, this happens naturally just in our DNA. These things fit together and these can be changed. Next, you need a way you can mutate or mate these things. So for us, this just happens naturally between generations. And last but not least, you need some sort of fitness metric. You need some way of determining which of these individuals is fittest, what should survive to the next generation, what should continue to propagate its genetic material. Now, there are a couple of challenges in applying this framework to censorship evasion research. So I'll walk through these step by step and take a look at building blocks. So first for building blocks. So ideally, we'd like Geneva to just run strictly at one side of the connection. So what we're going to do is we're going to manipulate packets to and from, in this case, the client. Okay. And the way we've built Geneva to be able to do this, we give it four building blocks. Okay. This is duplicate, tamper, fragment, and drop. And I'll call out two things specifically here. So duplicate, you take one packet, you have two packets. Tamper is exactly what it sounds. You take one packet and you change it in some way. Fragment, you take one packet and you split it, and now you have two packets. And drop, you have one packet and you drop it on the floor, and it's gone. And like I said, I'll call out two things specifically here. So for tamper, we let it alter or corrupt any TCP/IP header fields. And importantly, it doesn't have any semantic understanding of what these fields mean. So for example, if it goes to modify the flags fields, it sees the TCP flags field as something it can change, but it doesn't know that changing it to a SYN means the start of a connection. So syntax, but no semantics. And after it does an update, we will go back and make sure the packet is syntactically correct. We'll update the checksums, the lengths, etc. So second thing to call out is fragment. It does double duty here. At the IP layer, it will do proper IP fragmentation. At the TCP layer, it will do TCP segmentation. So now we have a system of building blocks. The next question is, how do we start putting them together? And this action system actually lends itself nicely to a composition. The reason for this is some of these actions introduce branching. So when you have tamper, you take one packet, and when you're done tampering it, you still have one packet. But with duplicate and fragment, you start with one packet, and you end with two packets. So what we end up having is that a tree-like structure is a nice way to put these things together. So here's an example of one Geneva strategy. We have a duplicate up here, and then there's two actions to the right of it, and these are two tampers. The last thing I'll talk to at the very top of this, every action tree has a trigger, and this is something that tells Geneva when to run this action tree. Okay, so this trigger specifically says if there is an outbound packet and the TCP flags is ACK, we should pull that packet into the tree. We'll duplicate it so we get two copies. To the left side, we don't do anything to it, we just send it. And then to the right side, we tamper it to make it a reset packet. We lower the TTL with IP TTL equals 2, and then we send it. So let's see what this will look like in practice. So here, once again, we have our intrepid client trying to make a forbidden request to a server. And it's about to finish the three-way handshake. So what's going to happen is Geneva is going to see this outbound packet, and it's going to see that it matches one of our triggers, and it's going to pull it into the tree. At this point, the packet is duplicated. Again, to the left side, we don't do anything. To the right side, it's tampered, and we change the flags to reset, change the TTL to 2, and then we do an in-order traversal of the leaves, and we send the packets that emerge. So we send this one first, off it goes, and then we send this one. And if you'll notice, this action tree exactly captures the strategy I opened with at the beginning. This is a TTL limited reset attack. And to prove to ourselves that this composition was expressive enough, we were able to go back to prior work and re-express all of those strategies with these building blocks. So this is the composition we have in Geneva. So next, I'll talk about mutation. This is where there are many different types and ways we can mutate these trees. I won't go through all of them here. If you're interested, you can check out our website or our paper, and we'll link to all of this at the end. But basically, we can randomly alter types, change values, merge trees together, split trees apart, etc. The last thing to call out is the fitness function. And fitness is basically trying to answer the question, which individuals should survive to the next generation? Okay. And this is basically a question of, in the genetic algorithm, what do we want to reward and what do we want to punish? So specifically, this is what we land on. We punish the system if it has triggers that don't trigger in any packets, and this encourages it to have precise triggers that match exactly what it needs to. We punish it if the strategy breaks the underlying TCP connection, and we do this as a search space reduction because it allows it to search just the space of strategies that keep the TCP connection alive. We reward it for successfully obtaining forbidden content through the censor. At this point, we could just stop. At this point, the genetic algorithm now has a sufficient fitness function that it could go and run against censorship. But we added one additional reward towards the end, and we did this for explainability, because we as researchers want to know and understand what this AI is doing. So we reward it for the conciseness of the strategy. So once it finds something that works, we reward it for simplifying it down for our simple human minds, so it's something we can read and understand. So this is Geneva in a nutshell. The building blocks, composition, mutation, and fitness. So at this point, I'd love to take you guys through some of the results that results from running Geneva against real-world sensors. So we've done this. We've run Geneva against 4 real-world country censors. So in China, against their FTP, DNS, SMTP, HTTP, and HTTPS censors. And this censorship operates by injecting content or injecting TCP resets. In Kazakhstan, against their HTTP and HTTPS censorship infrastructure, we've seen them inject content or just black hole your traffic. We've run against the HTTP censorship in India, where we've seen them inject block pages. And in Iran, against their DNS, HTTP, and HTTPS infrastructure. We've called out DNS especially in Iran because in all the vantage points we had access to, we noted that DNS over TCP was completely uncensored. So even though DNS over UDP was censored, just by switching the transport protocol, you could evade censorship, which somewhat simplifies the problem. And this is what this looks like. So you can kind of see that China has this impressive feature-rich censorship system, whereas India's is a little more simple. There's a wide diversity of censorship types and censorship protocols. Okay, so for the results for these, overall from the client side, we've been able to find 6 species, 13 subspecies, and 36 variants. And I'll call out what this means. We ended up finding so many strategies that we needed to define a taxonomy for classifying these things. So what we do is we call a species the underlying bug, the overarching bug of how Geneva is defeating the censor. Within a species, we have subspecies, which is basically how Geneva exploits that bug. And then we define variants, which are, they look functionally different on the wire. And looking at these are how many we find for each of these countries. It's actually kind of interesting because if you look at these numbers, you could get the impression that like China is really not doing so great with 31 strategies we found, and India is doing amazing with only 6 strategies. And this can be somewhat misleading because this really speaks to not how well the countries are censoring, but the complexity of their censorship systems. So China's censorship system is significantly more complex than India's, at least from the vantage points we were able to test. And that complexity breeds a larger attack surface. So India has such a more simplistic censorship system that the attack surface was just smaller, and it wasn't as feature-rich or interesting attack space for Geneva to explore. So at this point, I'm going to walk through some of the client-side strategy we found specifically. Some of these can be kind of fun and interesting. So the first thing I'll talk to is the turnaround species. This is something that is still functional today in Kazakhstan. This was actually originally identified by researchers several years ago in China, and China has since patched it. But today it still works in Kazakhstan. What this looks like is we have a trigger that fires on outbound TCP packets that are SYN packets. So basically at the very start of a connection. And all you do is you duplicate it, and to the first one, you change the flags to SYNAC. And what this ends up doing is you send a SYNAC packet before you send the SYN. Obviously, this is totally not real TCP behavior, but when the censor sees this, it's tricked into thinking that the client is actually the server. And in the mind of the censor, the roles of each side of the connection is switched. And because it treats content from the server differently than it does content from the client, this is alone is enough to beat censorship. Another fun one we've got to explore, we call a segmentation species. Basically, you take the outbound pushback packet. This is something that still works today in China. You fragment it twice at the TCP layers. This is segmentation. Once at index 8, and then again at index 4. This performs 2 segmentations. We first saw this, we thought this was very strange that this should work. Because the Great Firewall for a long time, last 8 or 9 years, has had the capacity to reassemble TCP segments, and people thought its capacity was flawless. So at first we're like, well, maybe what's happening is it's just taking this censored word, and maybe the strategy is just splitting up the censored word in a bunch of ways, and the Great Firewall can't recognize it anymore. And what we find, that's not the case either. When we perform this strategy, this is what our requests look like. The first 8 bytes, 4 bytes, and the remainder. And if you look, the full censored keyword, in this case, ultrasurf is a censored keyword in China. The full keyword is sent in the clear, unprotected, no other modifications to the packet. But based on how this is split up, the Great Firewall of China can no longer identify it as something it should censor. And what's kind of fun here is we've actually identified that this bug has some bounds. If the first packet is less than or equal to, or if it's less than 8 bytes, it does not work. And if the sum of the first 2 packets must be greater than or equal to 12. There are some additional constraints in our paper, but if you can set up your segments in such a way that you can hit this case deterministically. Frankly, we do not understand why this strategy works. We hypothesize that we're breaking some sort of regex match inside the Great Firewall by doing this segmentation, but we're still not sure. So if you end up playing with it and figure it out, let us know. But the ability to find these complex strategies in domains that humans had previously thought were perfect or not worth exploring drives home why it's so important and useful to develop an automatic tool like Geneva. For the last 9 years, Great Firewall has been able to reassemble segments. So this is not a space that humans have spent time exploring. Okay, so up until now, everything we've talked about has been client-side strategies. So this is running Geneva inside the client within the censored regime. The main issue with this is really deployment. It's getting Geneva to those clients. And that can be kind of tricky. Now, one thing we realized is we have Geneva, we have this ability to run on just one side of the connection. Why don't we just move Geneva from the client to the server and defeat censorship from the client side, from the server side? Now, this sounds ridiculous, but if this was possible, this would be a really powerful primitive for evaders. Clients wouldn't have to download any software. There'd be plausible deniability. And for a single server, we could broaden reachability of the software without requiring any client-side deployment. Many clients could connect to our server, and if the server strategy is successful, all of those clients would be able to connect successfully. Clients wouldn't need any technical expertise, and the server would just subvert censorship on their behalf. So it sounds awesome. The problem is it shouldn't be possible. And the reason for this is couched in what goes on in a TCP connection up until you send your forbidden content. So here's an example of a waterfall diagram of a 3-way handshake between a client and a server. Okay, the client's going to send a SYN, the server responds with a SYN-ACK, and the client sends an ACK. This is the famed TCP 3-way handshake. Then immediately thereafter, the client sends its censored keyword. So from the client's perspective, if it's going to manipulate the packet stream in such a way to defeat the censor, it has a whole lot of time to do so. It can change the SYN, it can send packets before the SYN, it can manipulate the 3-way handshake, or it can even change the query itself. From the server, though, that window is significantly reduced. The only thing the server does before the client gets censored is it sends a SYN-ACK. That's it. So our opportunity to affect change in the 3-way handshake or manipulate the response, the window is just significantly smaller. So this really, it's something that should not be possible. Fortunately, we didn't tell Geneva that it shouldn't be possible, and we tried it anyway. What we ended up finding was we found 8 strategies in China. We found 1 that works in India and Iran. And we found another 3 that were successful in Kazakhstan. So we're really excited about this. Unfortunately, I can't take the next 2 hours and walk through every single one of them. So instead, I'll just call out a couple. And again, if the demo gods are with us, I'll show off one of these. And again, none of these require any sort of deployment from the client side. They can strictly operate from the server. So here's a reminder of what our 3-way handshake works. And I'll walk through some of these. So the first one I'm going to talk about is what we call the double benign get strategy in Kazakhstan. Ooh, that was fun. So we have our client and our server. And this is a little different. The client sends a SYN. And instead of the server responding with 1 SYN-ACK, instead what it does is it sends 2 SYN-ACKs. And on each SYN-ACK, it attaches an innocuous, uncensored GET request. Now, obviously, the client is not going to respond to a GET request that's attached to a SYN-ACK. But this is an example of a turnaround attack. The censor sees these double GET requests coming from the server. And this is enough for it to confuse the direction of client and server in its mind. And it now thinks the server is actually the client's actually server. And it's like, oh my goodness, I must have missed something. And this is enough at this point that the client can now make its query. And for the rest of this the rest of this flow can continue uncensored. Another such attack in China is a simultaneous open-based desynchronization. So this is based on an archaic TCP feature. We had to spend a lot of time reading the TCP RFC to understand some of these. And I'll walk through this. So the client starts by sending a SYN packet. And the server, instead of responding with a SYN-ACK, it responds with a SYN of its own. And this is called a TCP simultaneous open. After it sends a SYN of its own, it then sends a second SYN that's corrupted in certain ways. And then the client, when it gets the TCP simultaneous open, it sends its own SYN-ACK. And this interaction between the corrupted SYN packet followed by the client's own SYN-ACK is enough to desynchronize the server, the sensor from the connection. And again, from the rest of this flow, the client can communicate unimpeded to the server without having to worry about the sensor. And again, this doesn't require the client to do anything. This behavior of the client sending a SYN-ACK, it may seem strange, but this is default behavior of TCP. This is not any modifications we've had to make to the client. So at this point, I'd love to walk you guys through a quick demo of seeing this work live. So if the demo gods will be with us, I'd love to give this a shot. So please bear with me 1 second while I switch my screen share. Please hold.
This is really cool stuff. I mean, I'm very much excited about the idea of having a server-side based evasion that people don't have to install any sort of client or any sort of software, and you can just, you know, roll something out on the server, and boom, people are circumventing the blocking of some site. It's really, really great stuff.
Thank you. Alrighty, can we see this?
There we go.
Beautiful. All right, I'll zoom this in a little bit. Okay, so I've got two machines here. On this side, I have a machine in Kazakhstan. And on the right side, I have a machine in Amazon EC2. Amazon EC2 is running an Apache web server, nothing too fancy. And I'm going to make a request from Kazakhstan over to my EC2 machine. To protect the IP addresses of these machines, I'm going to obscure the IP addresses throughout this. So either reference them through environmental variables, or if there's logging, the logging will replace these IPs. There's no other modification going on, but just to be transparent, these IP addresses you may see on the screen are not real. So anyway, if we make a request to our Apache, the machine responds, and we got Uni rocks. So this is great. Now, if we change the host header, and this is Kazakhstan sensors based on the host header, we try and make a request for something they don't like, so for example, pornography, the connection starts timing out. And this is the sensor stepping in and blocking what we're doing. From the server side, though, we have the opportunity to start manipulating the packet stream. And I'm going to show off a third strategy, that something that works in Kazakhstan. And this one is during the three-way handshake, instead of sending one SYN-ACK, we will send 3. And on each one, we will just stick a small payload. So the structure of these strategies, Geneva expresses these strategies in its own domain-specific language. It's a little confusing if you haven't seen it before. Once you get used to it, it's OK. But basically, we're going to take the TCP SYN-ACK. We make a copy of it. We change the payload of the packet to something random, in this case, just ASDF. And then we make some more copies of it. OK? And at this point, we can now run our engine. So I'm going to set this up with a few small options. I'm going to tell the engine, please run with this strategy. I'm going to say our server is running on port 80. And I want you to run as if you're running on the server side. Now, there's 2 other things I've added here, this log debug mode, just so I can show you guys the logs of this running. And then demo mode is what's going to just obscure these IP addresses to protect our machines. So we'll kick this off. The engine is stood up and running. And to show you this working, we can make a request for example.com. And once again, this works. And then we come back over here, what we can see has happened. We've got our request. Here's our SYN. We catch the outbound SYN packet, and we make 3 copies of it. Here's our 3 sins. Okay. And then the client makes a request. And so you can see I'm not lying to you. Here's the example.com. And then we get our uni rocks. So now we can try this again, but instead of example.com, we can request with YouPorn, and this still works. So just like this, the server over here is subverting censorship on behalf of the client. Here's uni rocks. Here's our strategy running live on the server. And just like this, we can defeat censorship from the server side. And this is highly reliable. We can keep doing this, and this will continue to work. And to show you I'm not playing any tricks, I can shut down Geneva running the strategy. And if I try this again, this will just time out. So censorship is back. So this is just one demo of what you can do with the Geneva engine. You can really make it do any arbitrary type of packet manipulations. And there are many other strategies it could demo. But for the sake of not taking the entire afternoon, I'll hop back over to my presentation. And I'm happy to take any questions or do additional demos of this towards the end if people are interested. Give me 1 sec to get this screen share back going.
That's really quite impressive. And I would say for the people watching that the demo broke, and Kevin literally finished the setting it up like 5 minutes before we were gonna go live.
Yep.
So you know, like virtual round of applause.
Thank you. Thank you. Alrighty. So while we've been playing with these server-side strategies, it started to give us new insight into how these sensors operate and how they can work. So I'll give you an example for this. So this is just a table taken from one of our recent papers on this. And it details the success rates of all of our various strategies we found for all the different protocols we tested against. And reminder, all of these server-side strategies operate strictly during the TCP three-way handshake. What's odd about this is why are then different applications affected differently in China? In China, what we find is we have some strategies that work very well for some applications and very poorly for others. Things that can be very successful at defeating censorship for FTP may not defeat censorship at all for HTTPS. Things that are highly successful for HTTP and HTTPS may not work for DNS. And this is very strange because all of these strategies are operating during the three-way handshake, which means the sensor has no idea which protocol we're going to use yet. And what this has led us to develop is a new mental model of how Chinese censorship operates. Because really, the way we usually think about different applications sitting on TCP/IP stacks is this, where it's this very sane, we have these lower-level transport protocols, and then we sit our applications on top of them. But really, what's happening is we have separate machines with different stacks underneath for all of the applications they're running. And it appears that they're running multiple censoring middle boxes in parallel. And this is kind of cool because what it exposes to us is this really diverse attack surface at these low levels. And this raises the question also of how does the sensor know which one to apply to a connection? If anyone's played with the Great Firewall, you know that it's going to catch you no matter which port you use. So what appears to be happening is they seem to be doing some form of protocol fingerprinting. And what this means is when a connection goes out, all of their censoring middle boxes in parallel are all tracking your connection. And as soon as they see something that doesn't match what their assigned protocol to censor is, they stop listening. What this means is any basic protocol confusion could be very highly effective against these things. If you're starting to do an HTTP request, but you make it look like something else, the HTTP censorship middle box will just stop paying attention to you. And this really has opened the door for a lot of other interesting questions to explore this new attack surface. Another interesting thing I'll call out here is we've been running into censorship-in-depth and letting Geneva run against censorship-in-depth systems. So earlier this year in February, Iran very quietly launched a new system, a protocol filter or whitelister. And basically the way this works is that any connections that do not match specific protocol fingerprints are censored. So on port 80, if you try and make a VPN request and your connection goes to the whitelister, it will take down and it will censor your connection, even if what you're doing with that VPN is fine, just because your connection does not match the fingerprint it's checking for HTTP. What this means is they have these multiple independent censorship systems also operating in parallel. Again, we put Geneva at this, and we were able to find 3 strategies to evade this secondary filter. And this has kind of also opened the door for other really interesting things, where using Geneva strategies, we can choose which censorship system we would like to defeat. None of these 3 strategies that work against the whitelister are successful against the standard censorship system. And none of the strategies that work against the standard censorship system are successful against the protocol filter. So what this means is we can compose these strategies together and beat both of them, or we can use just one or the other and study just one of the systems in isolation while defeating the other one. So this has been a really interesting exploration for us into fighting censorship in-depth systems, and we expect these to be start to get more prevalent. As we deploy this, the systems like Geneva have the potential to fast forward the arms race for both sides. So what usually would take humans many months to identify can now take hours. So the question is, like, where is this going? What we think for sensors, small bugs in implementation, we believe these are more low-hanging fruit. These are easier things for sensors to find and fix. But really big gaps in logic or systemic problems in how the sensors are built, we think these will be harder. So this leads us to ask the question, what is the logical conclusion of the end race? And what we believe is releasing the Geneva code and developing these automation systems can really help the evaders at the end of the day. Of course, the sensor can download our tool, and they can run it against their own systems. Really, there has been nothing stopping them from fuzzing their own systems 20 years ago. But democratizing this and giving end users the ability to run and understand and poke at these sensors, we think will really give end users a leg up in the end race. So I'm going to conclude just by thanking the entire Geneva team. This project really is standing on the shoulder of giants, and it's taken a village. But thank you, everyone. Some of you are in the audience, and for all those who couldn't be here, I really appreciate everything you've done to get this project off the ground. So with that, I'll conclude, and I'm happy to take any questions.
Thank you, Kevin. Thank you so much for that really interesting presentation on, I guess, really some groundbreaking work that your team is doing.
Thank you.
So we've received some questions from IRC. I'll remind you that you can, as usual, leave your questions in the YouTube chat. You can leave your questions on the UNI Slack channel, or which is also bridged with OFTC on the #UNI channel, or on a pad that we have set up that you can see the link here below. The first question comes from David F. And his question is, how did you hit on the duplicate tamper fragment drop blocks? Did you experiment with other options that were not as effective?
Great question. Yeah, so defining the action space for Geneva was actually one of the key insights for this. If you think about it, there's a lot of different ways you could give an algorithm manipulating packets. Like we could have it manipulate any bits. We could have it just encode results from previous evasion strategies and operate on those. We really landed on those 4 just based on what the IP header can do. We didn't explore too much in either direction because it's somewhat a slippery slope of, if you give it too many degrees of freedom, it could take a very long time to, like you can imagine if you give the algorithm, instead of just these 4 building blocks, just the ability to manipulate any bit. That could be very effective, like it could learn anything. But it could take it an inordinate amount of time to do anything real. For example, like you could imagine it trying to learn a checksum could take forever. On the flip side, if we made an even higher level and composed these things further, we could have given the algorithm, like instead of the action being duplicate, it could be inject a reset packet. We think that would also be successful, but that starts going down the slippery slope of we would be encoding our own human bias into the system. And we'd be telling it, hey, this is something that's useful as a primitive. So we think the balance we've landed on is a good fair shake between sufficient degrees of freedom to find really strange strategies like some of the ones I showed, while also not taking an inordinate amount of time to do anything and not encoding our own bias into the system. Good question, though.
Thanks. We have another question that comes from Federico. And his question is, some libraries and some hardware, for example, high-end routers, break the isolation between the TCP/IP layers for performance reasons. Do you suspect this could be the case for censorship devices?
That is an excellent question. The answer is I don't know. We haven't thought about that too much, but I'd be really interested to check it out and talk with you more after this. Yeah, I don't know.
Okay. Cool. I guess vaguely related to this, I also have a question, actually.
Sure.
And you mentioned at some point during your presentation, you talked about how you have like more variance, like the fact that you see in certain scenarios, like in China, that you have more variance for Geneva like evasion techniques that work, and that's somehow an indication that the system is more complex. And I found that a very interesting sort of observation, if you wish. And based on that, I was thinking, like, have you considered applying, like, using Geneva to find variants that work against a certain censorship system, to use it also to fingerprint it? So, like, could you apply, like, Geneva to understand, this is a characteristic of this censorship, and have you noticed that? And as like a way to link different like vendors or different systems that you see in various countries?
That is an awesome thought, and it's something we've been looking to do for a while. So the answer is yes. I definitely think we can. The bugs Geneva tends to find for these things can really be very idiosyncratic. So, for example, that segmentation species that works in China, that really very definitively identifies a Great Firewall of China middle box. Of the sensors we've studied, these four on the screen, we have not yet noticed any direct. These middle boxes look like they're performing the exact same way, or we don't see that right now. That being said, we would love, one of the things we're very interested in doing soon is dramatically broadening the training of Geneva and automatically trying to associate and cluster middle boxes based on the strategies that work against them. Doing that is a little bit tricky. It's a little tricky because of the amount of information that you glean from a sensor depends a lot on the strategy. Some strategies, for example, like simple TCP segmentation, there are a lot of different middle box implementations that can have that bug as successful, so you don't learn as much information about the middle box from that. Whereas there are some other ones, like in Kazakhstan, this double benign get, that's highly identifying. So coming up with a good way to cluster these is still very much an open research problem, but phenomenal idea and something we've been very excited to tackle soon.
Nice. Thanks for sharing that. So we have another question coming from Zoo, and they ask, have you been contacted by any censored website owner who are interested in running Geneva on their servers? Have you evaluated the cost for a web server to run Geneva?
Great question. The answer is we've reached out to a couple folks, and we've been in communication with some groups who I'll not name here. So the answer is yes, but we're absolutely looking for more groups to come chat with us. We think also deploying these strategies, the costs associated with them is we're not 100% sure what that looks like yet. The code to do this, like, it's all written. The demo I did today, all that code is public. You can take it right now and throw it up on your web server and see what happens. Really, the main barriers to deployment are this system is a beta research system. It's not designed for like an Nginx amount of load. It's written in Python. So the load barrier may be some small barrier to deployment. The second thing is all the training we did for these sensors, we intentionally tried to isolate. So it was just one machine talking to another machine through the sensor with no other competing middle boxes or firewalls along the way. Unfortunately, the real world is much messier. And it is entirely possible that the strategies Geneva identifies that mess with the sensor also mess with flow tracking for other middle boxes along the way. So we have in some small networks identified cases where we can defeat censorship, but in the process of defeating censorship, we also take down or impact another middle box's ability to carry on the connection. So I think there's a whole second field of work dedicated to training Geneva in a more complicated landscape where it needs to both defeat the censor, but also keep alive all the other middle boxes that may be on the path. That's a much more challenging problem that we have not yet probably come up with a good solution yet. So we're still working on it, but those are the things I imagine one would have to solve in order to deploy these things very broadly. That being said, if you want to reach out to us and chat with us, we'd be very happy to. And I'd love to walk anyone who's interested through how to deploy these things and what that might look like.
Great, thanks for that. And on this topic, I see Leonid left a comment on the channel mentioning that another problem that might be considered in deploying it server side is that it's hard to be behind anti-DDoS providers and also running something like Geneva at the same time.
That's an excellent point.
So, but I mean, it's research, so
exactly.
we're gonna get there.
Exactly.
So another question comes from Gus. Do all users have to run the process to discover strategies, or is it exclusively done from vantage points and then the strategies are rolled out to clients?
Great question. It is the latter. So the Geneva is set up in two broad components. There's the genetic algorithm that goes ahead and trains against these sensors and learns things. And then there's the component, we call it the engine, that takes a given strategy and applies it to a connection. So the model we've been operating under is that we as researchers will get vantage points or train against sensors ourselves and take on the risk of training against sensors. And then once we identify strategies that work, we can distribute those and give those to people who want to use them. That being said, the whole system is open source. So if you want to run the genetic algorithm yourself, you're free to. But you don't have to run the genetic algorithm in order to use the strategies Geneva identified.
Nice. Thanks for that. I guess I have another question as well.
Sure.
I guess going back to the topic of the variants and how you can use them potentially also to classify devices. Have you noticed the techniques or the strategies or the variants that work in a particular country or network to change over time? Have you discovered some algorithm that it's working, then it suddenly doesn't work, or maybe something that previously wasn't now starts working?
So that's something we have absolutely seen with strategies from the past. So researchers, for example, the turnaround species I talked to, I think right here, this used to work in China, and we call these extinct when they used to work somewhere and they were all killed off by the censor. So we absolutely see cases where there were strategies identified from past researchers that have since been killed off. I believe it is the case that all of the strategies we've announced publicly are still operable. So to answer your question, we've seen strategies go extinct in the past. We have not yet, these strategies that we've been tracking, these have not yet gone extinct. As time continues to progress, we've been monitoring these closely, and it will be very interesting to see if there are certain classes of strategies that sensors can patch or make extinct faster than others, or if some continue to live on very long. We think this is also going to be affected by how broadly these things are deployed. For example, if you have a strategy that no one uses, there's not much economic incentive for the sensor to invest resources in patching it. But if it's the case where you have many users abusing a feature in order to defeat censorship, suddenly that becomes a much higher priority for them to operate over. So it's the kind of thing where only time will tell. But it will be really interesting to see as these things start. Maybe they survive for a long time. Maybe they go extinct. We'll have to see.
Great. Thanks for sharing that. I have some comments. I'll read some comments from the channel. DCF mentioned how in relation to the beginning of your talk, when you were talking about DNS and TCP injection, he was saying that it's similar to what we saw in a session yesterday from Zach from IC Lab, who was talking about how DNS and TCP injection works, and referenced some papers that apparently TCP injection goes back to papers from at least 2006.
Yeah.
And the TTL trick also apparently is a very old school trick. There's a document from 1998 already talking about that.
Oh yeah. Yeah, this has been around for a long time.
So I found that quite interesting.
Yeah.
There's also, I guess, somehow an indirect question of how is the double bin, like good gets, working because the SYN-ACK can carry data, but clients incorrectly discard the data that happened before the handshake finished?
Great question. It works. So yes and no. The actual answer is it's OS dependent. Linux will discard those benign gets. So the strategy on this slide right here, this will work fine against Linux machines. Windows, in some cases, will not process this correctly. What we've been able to do to make this strategy work in other systems is if you just corrupt the checksum for these and then send a real SYN-ACK after it, that still defeats censorship. So from the client's perspective, there are different ways you can massage it so it works well with the client CCP stack. But really, it's just the presence of two back-to-back SYN-ACKs carrying a GET request that makes this effective against the censor. Does that make sense?
Yeah, I see. Interesting. Cool. You also mentioned some resources about the simultaneous open phenomenon, also called split handshake. There's some documents in the Nmap dev mailing list linking to that. I think they were also shared in the live chat, so you probably see
awesome. That. Yeah, fantastic.
Then, and David follows up now, says, I suspect it's something like that. That's interesting about the fact that it's OS dependent.
Yeah, there are a few cases we found where strategies work because of peculiarities in the TCP stack we ran against. This like SYN-ACK carrying data was really the main block we ran into between Linux and Windows. Most of the rest of the strategies, the TCP stacks were conformant enough that it didn't cause a problem.
Right. Another comment comes from Dave Levin, which maybe you know.
Hey, Dave.
It mentions that in reference to like outright blocking of IP addresses, which is something that Geneva is not well suited for.
Correct. Yes.
And that being something that requires an attacker in the middle, whereas most deployments appear to be on the side.
That is correct. Yes, there is this sort of censorship where there is the ability to drop packets destined to specific IP addresses still does exist, and this is something Geneva cannot fight against, because if the packets don't route to the server, it doesn't matter what strategy we do if there's no path to get there.
Right.
So thank you, Dave. Yeah.
So okay, we have some other questions coming in. So we have a question from Ram. The question is, have you seen any cases where a censor implementation has behaved differently from different locations, networks, or clients?
Great question. So the answer is we know this exists, but in practice, our vantage points so far have been sufficiently limited that all of the strategies we found, both server-side and client-side, have all worked uniformly across those vantage points. So for example, we had multiple vantage points in India, but those vantage points were located within the same ISP. So we were fighting the censorship of that ISP, and so the strategies worked for that ISP. That being said, we know that it is the case that for certain countries, Russia, Iran, India, to name a few, censorship is done in a very decentralized manner. It's not centralized like it is in China or Kazakhstan. And in that case, we think the attack surface between different ISPs or between different censorship systems or even the geographic location of your vantage point could totally change the game. We haven't run into that yet, and that barrier really has just been our own struggling to get a broad set of vantage points within countries. That being said, we're really excited to start ramping up the amount of vantage points we have in these countries and do a very broad training. For example, in India or Iran, if we got 50 boxes throughout the country and did all these trainings, or if users did training and reported the results back to us, we can start laying out a very interesting geographic-based map of the various bugs in censorship systems. So the answer is yes, but for everything I've presented here, all of these worked uniformly across the vantage point we have.
Excellent. We have another question coming from Liang. Now that you publish your strategies, What if the censor improves the middle box to catch, block all of these strategies? Is Geneva working because something similar to security through obscurity?
So great question. No, what we're doing is not obscurity. So I'll answer this in two parts. So the obscurity part first. In practice, you could imagine doing something where you had a Geneva instance running on both the server and the client. And on one side, you could base 64 the request, and on the other side, you could base 64 decode the request, or do all sorts of different tricks to obscure the request. That's not what this is. Like everything we're doing is understandable perfectly well by the other side's TCP stack. So these really are hitting bugs in the TCP implementations. That being said, you're absolutely right, and these things will likely not live forever. We don't know how fast these are going to be patched. And again, like I mentioned, all of them are still operable. If they do patch them all, it's kind of just game on. We'll run Geneva again and see what Geneva can find. All of these, every run here, every strategy I presented, Geneva identified in under 24 hours, and most of them were found in under an hour or two. So if it takes the censor 3 years to update themselves, and it took us 2 days to find new ones, that's a pretty good trade-off I'm willing to continue to bet on.
Yeah.
So really, we'll see what the future holds, and we don't know yet because none of these has yet been patched. But
Yeah.
we'll see.
And I see now they followed up as well with another question asking,
Sure.
have you thought of any aftermath impact to the censor if they block your strategies?
That's a great question. The answer is yes, and I think it kind of depends on how they go about doing that blocking. Because there's a lot of really, it can be somewhat tricky to block these things. I mentioned these different variants that we find where these things can look really different on the wire. So if you can imagine being a censor and you wanted to try and identify a Geneva strategy in action. You could imagine trying to write something like, if I see a reset packet immediately following the three-way handshake, and that TTL is different from the other ones, this might be Geneva, so I'll preemptively censor the connection, or something of that nature. So if they try and go down the detection route, that could be problematic because it's very easy for Geneva to just generate all sorts of different things that look different on the wire that do the exact same thing. So for example, that teardown attack I showed you at the very beginning, this guy here, where we send, here we go, where we send our own resets to the sensor. Even if the sensor adds special handling for seeing reset packets, Geneva also identified that you could set any set of TCP flags on the packet as long as the reset bit is set. So one of Geneva's favorite strategies that it routinely used to find in China was it would light up almost all the TCP flags. It would send like a fin reset act push UAE packet. It's like crazy set of flags. So if sensors want to engage in the detection game, that may end up being a losing battle because the breadth with which we can generate strategies that are still functional but look different may exceed their ability to write clean code that does that detection. Now, if they go down the route of we should just patch the underlying bug, depending on the bug, that may end up opening up different issues. So, for example, of these species, one of these species is just straight up simple TCP segmentation. So splitting the request into multiple pieces. And this affects middle boxes that don't properly reassemble TCP segments. So they could fix that by reassembling TCP segments and adding all of those features. But the problem is that exposes a new attack surface of, can you now desynchronize that reassembly? Or can you break that reassembly in certain ways? So it kind of depends on what the bug is that they're trying to fix and how they go about fixing it. But I think many of these like systematic things in the sensors that these strategies are finding could end up being quite difficult to patch. As another example, the reset attack I showed earlier, that's something that does still work in the Great Firewall. And I imagine that might be something that's difficult for them to fix. If they don't throw away state for connections that are closed, they could really face a pretty significant state explosion problem. So I'm sure there are ways, if they applied their minds to the problem, they could come up with solutions to it. But I think it's trickier than it sounds, and it'll depend on the strategy. I hope that answered your question. That was a lot of words.
Great. Thanks for sharing that, Kevin. And I see somebody followed up on IRC mentioning regarding the disclosure of strategy. There's a paper from Katak 2013 at FOCI that makes the good point that some vulnerabilities are harder, more expensive to fix than others.
Absolutely.
And ways that users can alter network traffic that will both avoid detection and crucially require the sensor to make expensive changes to the system's basic model to remedy.
Absolutely. And actually trying to encode that in a fitness function is something we've thought about trying to do, of encouraging Geneva. It may be able to find these like small littler bugs, but encouraging it to look past the smaller bugs to the really harder issues to find. Encoding that automatically can be kind of tricky, but that's something we've thought about to try and make that determination automatically.
Right. Okay, so we have another question, comes from Federico. Have you tested Geneva against commercial web application firewalls and IDS, IPS devices that you own or otherwise control?
We have not, and we're very excited to. It's on our short list of things to play with soon. If you have some targets in mind, hit us up and let us know.
Nice. Then we have another one, comes from Pepper JK. If you can host the genetic algorithm on your server, could those hosts use federated learning to contribute to the main instance?
Really interesting thought. Possibly yes. And that might be the direction, like this federated or distributed training might be a route we start having to go down in the future if the genetic algorithm ends up being a too complicated or too computationally expensive problem for one user to solve, or if they just want to diffuse that out. For now, the way the system is written, it doesn't work like that, but really there's nothing stopping you from doing something like that. So it's a great idea. I'd be excited to see it in practice. We just haven't written it yet.
Nice. Okay, last question we have coming from DWY. The Chinese VPNs seem not to be open to foreigners. Any suggestions on accessing Chinese internet to do experiments?
That's a great question, and getting vantage points historically has actually been our biggest blocker. Really, getting hold of machines within countries has been one of the trickier parts of this. Once we've written Geneva, getting machines is hard. So to study the Great Firewall, fortunately, if you want to poke at it from the client side, the Great Firewall, there are other examples of this, but to talk to China, the Great Firewall censors, we call it bidirectionally, which means it doesn't differentiate if you're a client coming from China, from inside of China, or outside of China. So if you want to try and trigger the Great Firewall, you can make requests to IP addresses destined inside of China, for example, to Baidu, and just craft them in such a way that it triggers the Great Firewall. So if you want to poke at the Great Firewall gently from afar, that is an option. That being said, vantage points obviously are the best way to go. And really, I unfortunately do not have a great suggestion for you to get a hold of them. If you have suggestions for me, I'm all ears, because vantage points are our biggest blockers as well. That's why there's 4 countries on this list and not 400. So it's definitely a tricky problem.
Well, unfortunately, that is all the time we have for questions. I would like to thank you so much again, Kevin, for joining us today and presenting this great work.
Thank you, Arturo.
I would also like to thank the rest of the team at the Geneva project for the really important work that all of you are doing in advancing the field of censorship circumvention. It's really great stuff.
Thanks so much. This has really been awesome.
I would also like to thank everybody who tuned in today for the live stream and followed this presentation, and also the ones that perhaps are viewing this presentation in the future. I'll remind you that tomorrow we have another presentation, which is actually the last presentation of the Internet Measurement Village, unfortunately. And yeah, it will be joined by Ramakrishna from the IOTA project, and he'll be telling us all about how they're examining internet blackouts through open data. So we'll see you there tomorrow. Thank you all for tuning in.
Thank you, guys.
Have a good night. Bye.